Welcome to qnawire.
Okay, we're supposed to write down a Lagrangian for this system. We have a mass big M that slides back and forth on a frictionless rail, and then a mass little m that's hanging from that and swinging back and forth like a pendulum. Okay, and we're supposed to write out a Lagrangian for this. The most important thing to remember about writing out a Lagrangian is that when you figure out the kinetic energy term, that you have to relate it to um, an inertial reference frame. And because this mass little m is attached to a mass big M that's sliding back and forth, the mass big M is not an inertial frame. It's non-inertial because it's accelerating back and forth. So you can't just write out, it's not that trivial to just write out the kinetic energy. You just have to be careful when you do that. So I'm going to define these two other variables called x1 and y1. Y1's okay non-inertially because it only depends on angle. It doesn't depend on x. So y1 dot looks like that. X1 dot looks like that. Okay, and then our kinetic energy term. So little x is fine as an inertial value when we're thinking about the kinetic energy of big M. We have to use x1 and y1 when we're thinking about little m, and we have to write them in terms of our actual generalized coordinates x and theta. Okay, and then we can expand that. And then our potential energy just has to do with how high the spring is. And I'm going to specify my zero gravitational energy up here at the wire where our big mass is sliding back and forth. The gravitational potential only affects the hanging mass and not the sliding one. And that's what it looks like, because it's really just mgh with a minus sign, because I'm putting my zero up at the wire, so it's below that mgl cos theta. So my Lagrangian looks like this. Okay, so there's the Lagrangian. So now let's figure out the equations of motion. So first, the x equation. We need the derivative of L with respect to x dot. Okay, and the partial of L with respect to x is 0. And so we get an equation of motion where we take the time derivative of that. I'm not actually going to evaluate that time derivative. I'm just going to write it out like this. Because here's the thing. Because it equals 0, there's no potential term in x. So the time derivative of what's inside there is 0. So this thing, big M x dot plus little m x dot plus ml cosine theta theta dot, that's a constant of the motion. And we'll be able to exploit that later on. For the theta equation, so that was the x equation. For the theta equation, partial L partial theta dot partial L with respect to theta. Now it does depend on angle, but only in the potential energy. Well, it's got an angle dependence in the kinetic energy, because of the 2L cos theta x dot theta dot term, and it has another angle dependence in the potential energy term. And so this equation, again, I'm not going to take that time derivative. They'll just be messy. And I'm going to want to simplify the equation first before I do that, since we're mostly interested in small oscillations. So there's my second equation. And like I said, I can expand this and take those derivatives if I want to, but there's no real reason to do it. So for the next part, for small oscillations, so theta is small, x is small. So really, it's not x that's small, it's x dot that's small. So we're just going to, x could be fairly large because it's measuring from some kind of arbitrary zero along the line. But what really matters is that x dot is small, so it doesn't have much x velocity. But there's nothing's proportional to x anyway, so there's no x squared to worry about or anything like that. Because theta is small, sine theta is approximately equal to theta, and cosine theta is approximately equal to 1, and x dot theta dot is 0, because that's a quadratic term, and we're basically getting rid of all the terms that are quadratic in our small quantities. So we get and there's a typo here. There's no m in the last term in equation 2. It should be an L. I'll correct that later on. So equation 1, which was the x equation, when we simplify it for small oscillations, looks like this. And equation 2, and that should have an ML out in front too on that G term. So equation 1, remember I said that has something to do with a constant of the motion. If we look at that, it really looks like momentum, and it is really the x component of momentum of the entire system. The y component doesn't matter so much because the actually y component of momentum is not conserved, because the little mass is swinging back and forth, and so it's going up and down all the time. But the x component is. And so we have this P, which is the x component of momentum, and that's a constant of the motion. And we can write x dot in terms of it. Okay? And now I can put that back into equation 2. Okay. And I can take my x dot from up here, take its derivative. I lose the p term when I do that because p is a constant. And so I'm going to get an equation for theta double dot, really, the second derivative of theta. And there's an ML thing that goes on here on the G term. Yeah, I really messed up that ML term. In the G term. Okay. Yeah, like I said, there's an ML here to make the numbers, to make the units work out, actually. But theta is some oscillatory thing involving cosine, and so we have a arbitrary constant for the magnitude of the amplitude, and another arbitrary constant for the phase. We're not given the initial conditions, so we can't evaluate those. And this is what it looks like. There should be an M here. I'll go back and put those in. Like I said, theta, M, and phi are arbitrary constants. And the answer to part D is that P is a constant of the motion, which means that our oscillations effectively are around the center of mass in the x direction. So as the one mass moves to the right, the other one moves to the left, because our x component of momentum is conserved. So we have motion around the center of mass in the x direction. So the x coordinate of the center of mass is fixed. Okay, so that's what's important. We have to remember there's a little m here and here and here and here. But these are right. So the omega is correct. And theta, m, and phi are arbitrary constants. And there it is.